Hello students, welcome to the EN 401 lecture on beam internal forces, shear and bending moment diagrams. Here's our roadmap for this lecture. We're going to talk about internal beam forces and how they flow. So those two types of forces are normal forces and shear forces, and we'll also see how beams fail due to normal and shear forces. Then we're going to talk about how beams flow internal moment and how they fail due to internal moment or bending. Then we're going to look at our shear and moment diagram sign convention, and then lastly we'll get into drawing our shear and moment diagrams for beams. So far with our beam analysis, we have covered external forces and moments that have been applied to beams, and then we've also studied how those beams, where they're connected, we studied the reactions at those connections, right? So everything that we've done for beam analysis so far has been external, so applied forces, applied moments, and reaction forces and reaction moments. So we need to answer this sort of big question here. So how do the external forces and moments, essentially how do they flow from where they're applied to the connections within the beam, right? And then how is that, how do those get distributed in the particles of the beam, and then how do we use that to eventually design the beam? Right, so this is the question that we're going to try to answer in this lecture: is how do forces flow in a beam due to the external loading and reactions. All right, so the first method that forces flow in a beam is just via this our normal force, right? And we've sort of seen this already with some two-force members, so cables in tension or short compressional objects in compression. Right, so our normal force flows in a fashion that is perpendicular to the cross-sectional area. So this happens in beams. We get normal forces that flow perpendicular, to the cross-sectional area of the beam, right? And so when we have normal forces that cause failure, we'll see a pull apart like we have here, or we'll see a crushing like we have here. You can also watch this video here of a concrete cube that gets crushed. It's pretty cool, so highly recommend. So that's the first way that forces flow in beams. All right, the second way that forces can flow through beams is via shear, right? So we have, in this picture down here, we have a load P in the Y direction. And that load P, if we were to evaluate that load P on this area here, right, we would see that it's acting parallel to that area, right, and therefore we're getting a shear force and a shear stress. Right, so beams have to be able to flow shear, else what will happen is the beam will fail in such a manner where one segment of the beam will move vertically down relative to the other, or the other might move vertically up, just depending on how the beam is loaded. Right, so this is kind of a graphic that shows you that how and why beams need to flow shear. If they don't flow shear, they'll fail like this. And we'll see some failures on the next slide. All right, so here we have some examples of some shear failure. So we'll just kind of go from left to right and look at these. So in this left picture, we have this block here, and we can see that that block has moved vertically up as compared to this block, or this block here has moved vertically down compared to this one, right? So this is a shear failure here, and we would call this our shear plane. Up here on the top right, this is a pretty easy one. We were pulling this way and this way, right? And we have failed this bolt and shear, right? This bolt should be straight, but it's not straight anymore. If it was connected, it would be connected sort of like this, right? So we had vertical displacement of one side compared to the other. And we got the same thing going on down here in the bottom right. this part of the beam has moved down vertically relative to that part, right? So this is a shear failure. Again, that would be our shear plane. Go ahead and watch this exploding beam video. It's a video of a beam failing due to shear, and you can see it's a pretty intense type of failure. All right, and then the third way that forces flow through a beam is via the internal moment. All right, so we have shear, we have normal force, and we have internal moment. And what the internal moment is going to end up doing to our beam, it's going to cause it to bend, right? So if we have an internal moment in a beam, we'll see some bending. So in this graphic here, we have what's called a simply supported beam. So pin, roller, we'll just imagine that there's a force right here, and our beam is bending. Right, so we're not applying a moment, but we still have an internal moment in the beam, and we're going to see how that internal moment flows in the beam once we draw our sheared moment diagram. But we can see here with this internal moment in the beam, we get bending, and then in this type of bending, we see tension in the bottom, which gives us pull apart fractures here in the bottom, and we see compression in the top, which is going to give us some crushing in the top. So our beams need to be able to resist bending stresses and bending failure, else they'll pull apart in the bottom and crush in the top. So again, big point here, second bullet, there does not need to be a reaction or external moment for there to be an internal moment, right? It does not need to be an external one for there to be an internal one. And this example here shows you that we get bending and an internal moment without an applied moment. All right, so here's some examples of bending failure. So going left to right again. So we had this applied load here, and we can see that we have a bunch of pull apart cracks here. So this is in tension. We can see that this area here crushed, right? So that would be in compression. So this is how we know we have an internal moment, because we're getting this bending, right? This beam is not straight anymore, it's nice and bent. We've got the same thing going on here. We can see it pulled apart here and crushed there, and this beam is clearly bent significantly. And then the same thing is going on here. We've got a bunch of pull apart cracks here, and you can see this beam is also bent. So that would be failure due to internal bending moment. All right, so let's put all those different flows together so we can see how we're going to end up designing our beams and seeing how everything works together. All right, so the first thing I want you to look at is this bullet here, and just rationalize this, that the particles of a beam are fixed to the particles next to them. Right? If they weren't fixed to the particles next to them, let's say they were pinned together, it wouldn't be a very good beam, right? You could just kind of bend it around. Right, so when you have a nice solid beam, all the particles are fixed to the particles next to them, right? So remember from our last lecture that fixed connections resist three types of forces. They resist forces in the x direction, forces in the y direction, and they resist that internal, or they resist a moment, right? They have that reaction moment. So a fixed connection resists all three of these guys right here. So let's see what that looks like in a beam. So we have a simply supported beam here, and it's already got this pre-selected cut here. So we're going to do a free body diagram of just this segment of beam here. This segment of beam here, right? So with this, actually I'll just draw a circle around it. So with this circled part of the beam, because this whole system is in static equilibrium, this system here must also be in static equilibrium. So we'll analyze that down here. So we know that the particles here are fixed, so this is our fixed connection. So a fixed connection gets a y force component, it gets an x force component, and it gets a reaction moment. and then we have a force P here, and then our reaction force By here. Right? So, so we can see that depending on where you may cut your beam up here, you can see that these values here might change, right? So let's say we were to analyze, a cut here, right? So if we analyze the cut here, this reaction moment would be smaller because it's closer to P. If we analyze a cut here, we can see that the reaction moment is going to be even smaller because now P, if we just analyze this piece of beam, there's not even an applied load in there. We just have By, right? So we can see that these values might change along the location of the beam. And that is the point of the shear moment diagram, is so that we can track what those changes are, and then we can properly design our beams. All right, so here's our shear and moment sign convention. So take a look at starting at the top left here, positive bending. So positive bending gives you a smiley face look here, right? So positive bending, your beam will have a smiley face look to it, and you'll see that in positive bending, a clockwise moment will be positive, and our counterclockwise moment will be negative, and that will be on our shear and moment diagram. In negative bending, we have a sad face. Our beam would look sad face in negative bending, and we would also have a negative counterclockwise moment and a positive clockwise moment that would cause that bending. Positive shear means that the right block will move down relative to the left block, right? So if we when we're doing our shear diagram, things that are forces that are up will be positive, and forces that are down will be negative. And the negative shear just means that the left block is going down relative to the right block. So negative shear isn't exactly less or better than positive shear. It just means which way blocks of the beam will move relative to other blocks. So the lowest value of shear is 0, and same thing with moment. The lowest value of moment is 0. So negative moments on our diagrams will just indicate negative bending, and negative shear would just indicate that the left block will move down relative to the right block. All right, so now let's get into the process of drawing our shear diagrams. And so the purpose of the shear diagram is it allows us to find the shear force at any point X, right? And so X will be measured typically from the leftmost connection. So if we had a pin and a roller, right? So X would be that distance that way. So at any point X along the beam. All right, so how do we make our shear diagrams? Well, we're going to analyze all of the vertical force components, whether they're applied or reactions. And the shear diagram is the integral of the vertical forces. So don't worry, calculus sounds hard, but it actually works out to be pretty easy. So we'll go through this. Big point here, distributed loads will cause the shear diagram to have a slope equal to the magnitude, right? So the slope of our shear diagram with the distributed load is equal to the magnitude of the distributed load. All right, so if you have a distributed load that is 10 pounds per foot pointing down, your shear diagram underneath that load will be negative 10 pounds per foot. All right, and then all of our shear diagrams we're going to plot from left to right. That way positive forces, forces that are pointing up will cause the shear diagram to go up, and then forces that are down will cause our shear values to go down. And then the other big point, the shear diagram always starts and ends at 0. So the sum of all shears should equal to 0. So if you start somewhere other than 0 and end somewhere other than 0, you've had an error either in plotting your shear diagram or your reactions are wrong. So you have to go back and recalculate. So let's go through how we do this thing. All right, so here's our shear diagram example. So first thing you'll see here that's new is this graph here. So let's call it G. We got a graph here for our shear diagram. All right. So on the y-axis, we have the value of the shear force, and on the x-axis, we have distance x along the beam. Right. So y is shear force, and x is distance x. All right. This line here indicates 0 shear. Remember, 0 shear is the least amount of shear. Negative shear just describes relative motion differently. So negative shear and positive shear are both equally bad, just would cause parts of the beam to move differently compared to other parts. And the last thing we see here is this dotted line. All right, so this dotted line indicates that we should see a change in shear where this applied load is at. We also see these solid lines here on the ends, and that's the bounds of our shear diagram. Remember, there can't be any shear outside of the beam, right? If we were to if we were to analyze some point out here, right, there's no shear in the air caused from the beam, right? And so that's why shear must always start and end at 0. Once you go outside the beam, there's no shear left, so it's got to end up back at 0. All right, so here's our process. So first we need to solve for our reaction forces. So this one's pretty easy. We've got a 1,000-pound in the load in the middle of a 10-foot beam, right? So AY and BY are 500 pounds, right? So half that 1,000 is going to either the pin or the roller. If you need help with that, feel free to pause the video and solve those for yourself. You can just take moments about point A here, and that will give you those answers quick. All right, so now that we have those, we can start plotting our shear diagram. So what we'll do first is we'll draw those forces on here. All right, so we got our AY and our BY, both 500 pounds, and we drew a nice arrow indicating that they're going up. All right, so now we have everything that we need to start plotting our shear diagram. And remember from that last slide, shear diagrams always start and end at 0. So we're going to start at 0 here on the left. All right, and we're going to analyze our vertical forces. And we're just going to go left to right looking at vertical forces. So the first vertical force we see is AY with a value of 500 pounds. So that's going to cause a shear to go up from 0 to 500 pounds. Right, so this is AY. This black arrow here is AY. And that has a value of 500 pounds. Sort of ignore this purple block here just for a second. Right, so we started at 0, we went up the value, straight up the value of AY of 500 pounds. All right, so remember, shear is the integral of vertical forces, right? So there's no vertical forces between AY and our point load here. So what happens is our value of shear is going to remain flat. So that's sort of why this box is here, to indicate that shear remains flat through that section at a value of 500 pounds. All right, and then we hit our load P, which is 1,000 pounds here, and we're going to make a very unsurprising move. Our shear diagram is going to go down by a value of P. So it's going to go down from 500 down 1,000 pounds to this point here to negative 500, right? So we're at 500 pounds of shear. We're going to lose 1,000 pounds thanks to P, and we're down here at negative 500. All right, once again, there is no vertical forces in this zone here, so our shear diagram remains flat. And then we hit BY here on the end, and BY has a value of 500, so we're going from negative 500 plus this value of 500 back up to 0. All right, so just kind of going through this again. So we started at 0, we went up the value of AY, which was 500 pounds. There was no forces between AY and P, so we remained flat on our shear diagram for this first 5 feet. Then we hit load P, and P drops us down from 500 to negative 500. So So this would be negative 500 here, and this is pounds, right? And then we're going flat because there's no forces between the P and BY here. Then once we hit the end here, we get BY pushing us back up to 0. So started and ended at 0. So this is good shear diagram. All right, before we move on, just a question for you guys to think about, right? So we know that on the y-axis here, shear is in pounds, right? Our y-axis is a shear force in pounds. And then our x-axis here is distance, and that's in feet. So what do you think the area under the curve might indicate to you? Right? We have, if we were to multiply those together, so the y-axis is in pounds times our x-axis, which is feet. Does that look like units of a moment? If you answered yes, you are correct. Right? So the area under the curve is actually going to indicate to us what our internal moment is along the beam in any section. We'll see that process in the next slide here. All right, so that last question was, what happens when you have a distributed load? All right, so we'll go through that real quick. So in this one, we have distributed load that's 100 pounds per foot instead of that 1 point load that was 1,000 pounds. So if we go ahead and solve for our reactions, we would still get the same reactions. AY and BY both equal to 500. So we'll put those on our pre-by diagram, and then we'll start our plot. So as you recall, when we do static equilibrium defined reactions, we resolve our distributed loads to a single point load so we can do our moment equation. But when we do our shear and moment diagram, we have to get rid of that point load and put our distributed loads back on for the plot, all right? Because the plots will end up being much different if you don't. All right, so let's take a look at this one. So same process, we start at 0, and then we're gonna go up a value of AY equal to 500 pounds. All right, but now we have a force between A and B, right? With distributed load, if you recall from the slide, we're gonna have a slope on our shear diagram equal to the magnitude of our distributed load. So our slope is going to be negative 100 pounds per foot. So we went up AY, and now we're going down 100 pounds per foot because of our distributed load. Right, our distributed load is 100 pounds over 10 feet, so 1,000 pounds. So we're going down a value of 1,000 pounds over the length of the beam, which puts us down here at negative 500, which is where we want to be because BY is 500 and brings us back to 0. So one thing to look at here versus just having that single point load is that, remember, that point load had rectangular blocks for area under the curve of the shear diagram. And just remember, if area under the curve of the shear diagram, if it's negative, is between the 0 line and the shear line, and positive is here, right? So with our distributed load, our area under the curve is these small triangles, whereas with that point load, we had large rectangles. And so the area under the curve of our distributed load is actually smaller. And remember that we can find moment, which is, the y-axis times the x-axis. And so you can see that our moment is going to be smaller because with this distributed load than the point load because the area under the curve is smaller. All right, so now that we're experts on shear diagrams, let's get into doing the moment diagram. So the moment diagram is essentially like doing the shear diagram, except instead of using the vertical forces, you're going to look at applied reaction moments, and then we're going to look at the shear diagram. All right, so the area under the curve of the shear diagram and applied moments are going to allow us to plot our moment diagram. All right, so the moment can be a little tricky, so make sure you know what your sign convention is, so that way you know if an applied moment is positive or negative. One case we see a lot is a cantilevered beam, right? See a lot of cantilevered beams fixed on the left end with an applied load out here, right? So this is going to bend like that, so sad face. So in cantilevered beams, we have a reaction moment like this. And that's actually going to be a negative moment, internal moment, because we get negative bending. All right, so just kind of remember that. You'll see that in the examples. So at our cantilever beams, with this negative bending, our internal moment will actually be negative. All right, so how do we do this moment diagram? What we're going to do is we're going to break up our shear diagram into small sections, and then we're going to find the area under the curve of those sections, and that'll give us the magnitude at various points along the beam, and then we'll just connect the dots. Same with the shear diagram. The moment diagram always starts and ends at 0, and sum of all moments is 0, right? There's no moment in the air outside of the beam, from the beam, right? So at the end of the beams, the moment must end up going to 0. All right, so let's take a look at a moment diagram. All right, so let's go through how we do our moment diagram. So for a moment diagram, we need our shear diagram, which we've already completed for this problem. So we're going to go ahead and throw that up there. So there's our shear diagram. Remember what I said, that shear, our units of shear on the y-axis is pounds, and on the x-axis this is going to be length or feet. So if you find the area under the curve of our shear diagram, that is going to give you the value of moment. All right. So we're going to break this shear diagram up into two sections to do our moment diagram. So we'll split it right there. So we have this positive section and this negative section, right? So let's, we've actually already got the area under the curve of both those sections. So our magnitude, or our height on this block here is 500 pounds. The length is 5 feet, right? So the value of moment throughout this 5-foot section here is going to get you to 2,500 foot-pounds. So remember, our moment diagram starts at 0 and also ends at 0. And before I click the next button, we'll just kind of look at the area under the curve of our negative block. So we have negative 500 pounds, right? That's our value of shears, negative 500 pounds. It's also 5 feet long. So our value of moment at the end here is negative 2,500 foot-pounds. So if we add up both of these, we see that our sum of moments is equal to 0. So as we're starting at 0, we're going to get back to 0. Let's just take a look at what that looks like. So because our area here is 2,500 foot-pounds, our shear is going to go up, our moment is going to go up to a value of 2,500 foot-pounds. All right. The slope of our line here is equal to the slope, or is equal to the magnitude of the shear directly above it. So each 1-foot section of this block is 500 foot-pounds, right? So our slope is 500 foot-pounds per foot. On this block, each 1-foot section has an area of negative 500 foot-pounds, so our slope here is equal to negative 500 foot-pounds per foot. Right, so our positive block takes us from 0 up to 2,500. And then our negative block takes us from 2,500 down 2,500 to a value of 0. All right, here is example 1. Go ahead and watch the video, and the solutions are in the following slides. Here's example 2. Go ahead and watch the video, and the solution is also in the slide. Here's example 3. So remember our fixed connection here. We're going to see negative bending, right? This beam is going to bend down. So negative bending. So that means our reaction moment when we do our moment diagram will be negative. So go ahead and try this. Watch the example video, and then you'll see the answer in the next slide. Here's example 4. Solution. Example 5. Example 5 solution, and example 6, which is pretty tough, and example 6 solution. All right, here's our review. All right, so the shear diagram is derived from the vertical applied and reaction forces. So if you have an angled load coming in, you will get no shear from the X component of that angle load, only from the Y component. All right, or if you have just a purely X component force, that would just be a normal force and has nothing to do with the shear. All right, big one here. When plotting that shear diagram, always use the original loading condition. So if you have a distributed load, go ahead and put that distributed load back on. Do not plot it with your resolved distributed load. You know, that one point load you made to do your moment equation. Get rid of that and then put your distributed load back on to do your shear and moment diagram plot. So the moment diagram is derived from the shear diagram and applied or reaction moments. And I didn't cover this too well, but applied moments will cause the moment to either go straight up or straight down depending on the sign convention. So if you have a cantilevered beam, like so, with a force out here and a reaction moment like this, that'll be a negative moment, so your moment will go start at 0 and go straight down because of that applied moment. All right, when applying the shear and moment diagrams, start from the left and work to the right. If you start on the right, things will be backwards and confusing, so up forces will go down and down will go up, and counterclockwise moments will be positive instead of negative. It's kind of difficult. So just always start from the left and work from the right. And big point, let's cover it again. Cantilever beams typically experience negative bending and therefore have a negative internal bending moment, right? Remember that bending moment on our moment diagram will cause it to go straight down. So we'll start at 0, go straight down, and then you'll plot the rest of it this way based on your shear diagram or any other applied moments. All right, thanks for watching.